So NMR actually stands for nuclear magnetic resonance spectroscopy. There's no S at the end, but spectroscopy is added in there too. Our chemistry relies heavily on NMR, and it's rare if I go less than at least 5 times a day. So I'm constantly walking up and down those stairs to get to the NMR. Atoms all have nuclei. Most nuclei have spins, which can be, they're typically represented as arrows when you look at a textbook, like up spin or down spin. And so they're generally in their resting state, their lowest energy ground state. When we put them in the NMR, we're putting them in a magnetic field that then excites the spins of the nuclei. And what the NMR is actually measuring is the relaxation of those spins back to their resting state. Because the NMR is a huge magnet, essentially, we can't get too close before we start to feel the pull of magnetic field if we have anything that's magnetic on us. So before you take an NMR, me personally, I'm always sure I don't have any credit cards with me, I don't have my keys, I don't have my watch on. The NMR gives us information, gives us structural information, it can give us information about the purity of the sample, about what some of the hydrogens that we're seeing are next to, and so it's a really powerful technique where we can look at a solution and we can visually see a reaction, but then taking an NMR, we can see what's actually happening at the molecular level. Generally, when we take an NMR, we should have some type of idea of what we have in our solutions. So we're looking for those types of something to distinguish whether a reaction is occurring and whether what is actually happening is what we want to happen. Most of the times that's not necessarily the case, and you end up with something that you weren't expecting, but those discoveries can then lead on to different experiments to try and other exciting science as well.